Quick warning, this video contains a lot of flashing images. So, I might either be about to find out something about this display that I'd not anticipated, or hopefully soon we'll have another video with me playing Doom on this display. Well, it's been 6 months and it's 80% done. It's not quite Doom, but it's been a hell of a journey so far. Let's go straight into what needs finishing here. So, straight up you can see the missing columns. There's 20 unconnected cathodes here, so we're displaying 80 out of 100 columns, hence 80% done. Hopefully I'll have those working very soon actually. You can see noise in the image, this kind of visual snow, particularly in the dark areas. It doesn't actually look that bad in person. I think it might be fixable through playing around with the refresh rate. It was obviously not there previously when the display just had text. The top 4 rows don't always work. That's something of a design flaw on my part, so we'll find out why that is in a few minutes. And I'm still using the original power supply board on the back here. You can see it's all a bit scrappy at the moment with a bunch of connecting wires. So I need to get that compactified, need to design that out onto a separate board, get everything into a nice slim form factor. However, I'm pretty pleased with where I've got to so far, and just getting here has been a lot of work, but I'll definitely finish this project now. It was originally going to be a 2-part series, these videos, but I've got a baby due in a few weeks. In fact, actually, hang on a second. So yeah, there we go. Actually, there's that's the ultrasound scan right there. It's quite a good image to display on this. So yeah, I thought I'd post this video update before I take that short break. So as you may have gathered, it's really difficult to film this display. It's very flickery or overexposed. I have to kind of compromise between the two. I think you get some kind of idea of how it looks here. Trust me when I say it looks better in person. You can choose to believe me or not there. So for the brighter images, a photo's kind of more representative of what I can see. But the video works better for the darker ones due to the noise. That doesn't show up as well on video. It's definitely not as clear in person either. So yeah, now I'm able to display a 100 by 100 pixel image, and it's 4-bit grayscale as well. And as I mentioned, we have those 20 missing columns. Some of the images work better than others, but what I found, and you might have gathered actually just with these sample images I've showed here, high contrast images of faces actually work surprisingly well. I think that's to do with humans being quite good at recognizing faces rather than the display itself. So as a demo of the capability for this video, I decided, I decided to use some face images. Where can I get a bunch of good high contrast images of faces? So I'm not capable of really using this display for anything serious. I think we saw that in the last video. So the obvious solution was to disappoint all my friends and family and turn this into a waifu viewer. And that was a fun journey. So here I am using a data set of anime faces from Kaggle. Put the link in the description there for you as well, actually. They generally show up pretty well, as you can see here. But why stop there? So I have these sort of saved on a computer just to display. It turns out a team of distinguished coders, these gods amongst men here, built a waifu API. So we can pull our images from there too, and there's some rather nice images. The quality's hit or miss on the screen. These ones do tend to be upper body shots, but hey, nice to have a bit of variety. So the way that I go about displaying these waifus on this screen is through an API which I actually wrote myself. So that lives in this Raspberry Pi here. And it's available as a Docker image for anyone wanting to attempt this themselves. Obviously, you can display whatever you want. You don't have to be ridiculous and use it as a waifu viewer. By editing the code, and I'll put some instructions in the GitHub account linked below. You can display pretty much what you want. I've still got the old code there for the vehicle tracker and a weather station that I use for the Numatron display. So pretty much whatever you can think of, you could display here. But JPEGs or PNG images, I've also got functionality to convert them, send them over to the API, which will then be available for the display to read, and then display in a grayscale image. So when I have it finished, I do want to display something actually useful, but I'm yet to decide what I'm actually going to do. I haven't really come up with anything, so I'm very much open to suggestions. But don't be that guy that throws the N-word around in the comments, by which I mean NFT, because someone's bound to have that idea. We're not displaying NFTs on this. By the way, I love how in my worldview, owning an NFT is far cringier than owning a waifu, which it absolutely is. To explain how this works, I have to recap the original design, how I originally received this display. So in its original form, it looked like this. Let's work our way up from the screen. So the screen here is a glass envelope containing 100 cathode wires and 100 anode wires. Applying 240 volts to an anode while pulling the cathode to ground causes the gas to ionize around the intersection and causes a dot to form, a bit like this. So if we want to draw a single row of an image, we can turn the cathode to ground and put the corresponding anodes to high or low depending on what we need. So we'd have something like this. And then to draw an entire image, we repeat that process and just scanning down all of the cathodes, scanning down each row like so. So these cathode wires are controlled from the first board, which is integrated onto the back of the screen. So let's take a look at that here. If we remove all the other boards from the view. Okay, so each wire has a direct connection here to a little tab on the back. And in theory, we could selectively connect these tabs to ground and have direct control of the anodes. But the board also contains these transistor arrays, a couple of dozen or so. And what these do is they allow us to use logic voltage to switch the cathodes. So those are controlled via 18 tabs on the tops of the board. So these that I've highlighted in red over here. By selectively applying 5 volts or 0 to these tabs, we can control any of the 80 connected cathodes that are connected to these transistor arrays. So that's how the screen was originally driven, by sending logic signals to these 10 on the top. So these 10 control which individual cathode is switched on, and the 8 on the bottom control which group of 10 is active. So by applying 5 volts to one tab on the bottom and one on the top, 8 times 10, we could control all 80 of the cathodes. Next is the anode control PCB. So in my design, this has been completely replaced, but it was originally connected via these ribbon cables to the anode wires directly on the front of the display. Each wire has a direct connection to the PCB, and it's then in turn connected to these 3 transistor arrays. So what these do is they allow us to use logic voltage to switch on or off any one of the anode wires. So by selectively switching them on or off, you could select which columns are active on the display, and therefore which pixels on an individual row light up. And then finally at the top of the board here, we had the logic PCB. So this converted input signals into something usable by the subsequent lower boards. So it's connected via these 15 lines here, which have now been entirely removed as well. So these passed down serial signals from the top board to the anode and cathode boards, which then performed the switching. Now, we're not that interested in this board. Most of it's been removed now. But this section at the top right here, that's the power supply. And for now, we're actually still using that to supply power to the screen. Here's how the project progressed since my last video. My first thought was to somehow swap out the ROM chip on the original logic board to allow us to display anything instead of just the pre-designated characters. The idea lasted for about 30 seconds. It would have never worked for many reasons, which I won't go into detail here. My second idea was just to replace the logic elements of the top board. So remember those 15 logic lines from the original display? Those can be used to send serial data to the anode and cathode driver boards and control all the connected anodes and cathodes. The original datasheet even tells us how to light up individual pixels via these lines. So there's 2 problems with doing this. I did briefly try. I could never really get it to work, although I didn't really try very hard, because I knew I was never really going to do this as the final design. I'd need another PCB just to connect up the missing 20 cathodes and 20 anodes, because remember, 20 rows and 20 columns were never connected on the original display. So at that point, I might as well just ditch the existing logic anyway and just design an entirely new logic board. So then the third kind of iteration was to build what I have now, a board which controls all the cathodes via the 18 pins on the bottom board, and which controls all the existing anodes directly via the on-screen connections, and deals with the logic. So finding a suitable chip to control the anodes was really difficult. I needed an array of transistors which could be switched by 5-volt logic to control 240 volts. The chips I chose were originally designed for plasma screen TVs. This was the board that I tried to incorporate them into, and it pretty much went straight in the bin. It had several design errors and didn't work. So revision 2 of this board didn't work either. Those chips were really difficult to solder, and ended up not working anyway. I'm not sure if it was because I couldn't quite get them soldered properly, or if it was because the voltage was just too high and they kept burning out. Another flaw with this board is I originally intended to use surface mount resistors for the current limiting. I designed it for 0603 size resistors, which are a decent size, they're easy to solder. Before I realised I'd actually mixed up imperial and metric, and these were 0.6 by 0.3 millimeter resistors. Absolutely tiny. Yeah, sure, I could solder them, but it'd take ages. So this kind of caused me to rage quit SMD components and design an almost entirely through-hole board, like the original, which I thought was quite a nice touch to the original anyway. At this point, I was really struggling to find a suitable chip for the anodes, and I realised that the solution was right in front of me the whole time. Just use the original chips from the original display. So these chips are actually quite awesome. They're like space-age Soviet technology that apparently we can't get anymore. Each is a 32-bit shift register which outputs into an array of MOSFETs which are capable of controlling the high voltages. There's one issue. There's 32 bits, 3 chips, 96 for 100 rows, so 4 short. So I filled the last 4 rows with optocouplers. And unfortunately these aren't perfect, and this is the reason the top 4 rows don't always light up. The refresh rate is just not fast enough for the purpose. So they work as on or off pixels, but don't work as grey pixels. So I'll look to replace those with transistors in the next revision. I had to reverse engineer the original board to figure out the inputs for each chip. I was amazed though when I soldered them onto this board, and they just worked first time. It's the only thing that worked well first time in this project, so that was a real bonus. My choice of microcontroller was actually quite critical too. Originally I was going to use an ESP32, but as I was redesigning the board, the Raspberry Pi Pico W was released. So I decided to use that instead due to a very special feature, PIO state machines. We'll talk about those in a second, but without that capability, the project would have been much more difficult. I'd have had to program in C, which I'm not very good at, and it would have just taken me a lot longer. I intended to use a standard nixie power supply, like this one here. But when I hooked it up, it actually failed pretty quickly. Now, I'm almost certain it's due to the higher than expected current draw of the display. I won't talk about why that is at length here, for now anyway. But for now, I'm just using the original power supply from the original display. I will eventually redesign it into a more compact board that could sit between the 2 PCBs. So for now, we have this main board which controls all the anode and cathode logic, and is hooked up to the power supply. Assembling this board does take a while, so I find it best just to put on a decent playlist or podcast and take your time. There are 200 pull-up / current limiting resistors which need to be arranged in a specified pattern, which I've kind of shown here my sequence for soldering them onto the board. You have to be very careful not to allow the leads to contact adjacent resistors or those on the other side of the board. That can let 240 volts bypass the current limiting resistor, and it caused me issues. Got a little clip here. A couple of the rows they were bypassing, and if I'd left it like that, it would have damaged the display after a while. It was also pretty difficult to design the paths for the anode control chips. We've got some footage here of me just dragging things around and designing the board. But since the connectors on one side of the screen are for odd anodes and the others for even, it meant I had to alternate the outputs between sides of the board, hence the mess. That's also why the PCB schematic looked like this before I arranged all the components. Now, another little complication was I had to do some very, very tense micro soldering to reconnect a broken anode wire. I mentioned that in the last video. We had one row that wasn't displaying, and this was why. So here it is after I'd connected it back up again. Now, let me tell you, going near a glass display with a hot soldering iron is always nerve-wracking, but it's done. Coding up this board turned out to be more difficult than I originally anticipated too. Originally I was planning on using an ESP32, but I switched to a Raspberry Pi Pico, as that was released in the middle of this project. So I've mentioned PIO before, so what is that? So the Pi Pico, in addition to the main CPU, has 8 kind of additional processors, or PIOs, which stand for Programmable Input-Output. They can run independent of the main processor and can be configured to switch pins on or off really quickly without interrupting the main process. You know what here needs pin switching on and off really quickly? A matrix display. For every row we need to shift in and latch 300 bits of data. That's 300 because it uses frame rate control, so each row is actually written 3 times per frame. So that's 30,000 pin writes, I suppose, per frame. I did start off trying to use just standard Micropython straight to the GPIO pins. I did that just via a standard shift register library, but it is way too slow. You could see it physically scanning across the screen. So I had to go straight to PIO, which is actually quite fun to program in for a while. You have to use this kind of assembly language to send commands to the state machines. It did end up taking me 2 days, but I got there in the end, and it works really nicely now, actually. I'd been wanting an excuse to use the PIO capability of the Pico for a while, so I was kind of too stupid to understand it quickly. It did feel really good to actually get it working. To get an image from a file on the computer to something on the display, all the processing takes place on the Raspberry Pi. So the raw image is fetched by the Pi either from file system or from an external API and loaded in as a NumPy array, and then it's converted to grayscale. Each row is then saved as literally a Python list of binary bits, 1s and 0s, and I split it into 3 32-bit words and 1 4-bit word, so that's 100 bits altogether, 100 columns. These are then just saved as a list of integers and posted to my API, which is published by the Raspberry Pi, as a JSON file. So we actually just end up with a list of integers that I can make a GET request to. When the Pi Pico makes a GET request to the API, it returns that list. For each row, the 4 integers are shifted into the shift registers, which we can remember just think of as one single 100-bit register, and latched to switch on or off the corresponding anodes. In reality, it's actually done 3 times per row with 2 separate binary images to achieve the grayscale. There's more info in that in a link in the description. That is the frame rate control. It took an awful lot of thinking about, by the way. I spent a long time worrying about leading zeros, which you don't need to worry about. The PIO resets the registers to 0, so you don't need to worry about leading zeros. Timings, there's a big fine line between having a really flickering display and one that keeps crashing due to the frequency being too high. No idea why it does that, by the way. A couple of the clips here, I think it does it. That's something to investigate in the future, I suppose. We're just about there. I'll post a part 3 of the finished display in the next few months. In order to do that, I need to build a daughter board to control the missing cathodes. The existing board was meant to do that via pairs of MPSA42 transistors, but it just didn't work. I don't really know why, but I've got a number of alternative solutions on the table. I need to make some improvements to the code. I'll get it all more accessible and easier to use, along with hopefully improving the display quality. I should really make this display video too, shouldn't I? Yeah, I'll do that. The power supply. So that'll be another daughter board to make the overall design smaller. I may or may not do that in the next video. That might be something for the future, because even just using the existing display, it still does work. It's just in a slightly larger form factor. I do need to replace the optocouplers for the last 4 rows with something faster. Again, I may or may not actually do this. It works okay for now, and it's something I might just do in the future and give a quick update on. Finally, I need to make a nice enclosure for it. I'll probably 3D print something. I might think of something else. We'll see what the overall depth, the thickness of the display is in the end. So as I said, this will get finished. I can't say exactly when I'll finish it, especially considering I'm going to be quite busy for the next few months, but I'll post a video when it's done. This has already been by far the biggest electronics project I've ever taken on, and I'm really excited about finally completing it. In the meantime, you can keep an eye on the GitHub repository linked below for updates, and hopefully some documentation and instructions. So thank you very much for watching, and I'll see you soon.